Am I audible and my screen is visible?
Yes, sir.
Okay. So shall I continue?
Yes, sir.
Okay. So thank you so much. First of all, a very good morning to you all. Sorry. So let me. So first of all, a very good morning to you all. I wholeheartedly congratulate Dr. Amvisha, Dr. Ajesha, and Dr. Shalini Singh. So for organizing this 1 week online STTP on recent trends in environmental geotechnics for sustainable development. So I really appreciate your efforts because this is a need of the hour as appraised by Professor Singh and Professor Amit. So Professor Singh, in fact, I'm very fortunate to have a PhD degree under his supervision and very fortunate to engulf a drop of knowledge from his ocean of knowledge. So today I'm going to talk a bit about the stabilization of extremely alkaline red mud waste for conversion into green sustainable materials. So just to appraise you, Professor Singh has given a detailed insight into what are the different problems so that normally you encounter when you deal with the waste material. In fact, he has given a thorough, a run-up of all the different topics on what topics you should work or on what topic you should search. But so we are not in such a position. So we are trying to work on a specific topic. So especially I'm trying to work on a specific topics like geotechnics and waste valorization. As you know, I'm in IIT Bhubaneswar, so in the state of Odisha. So, and this state is rich with minerals, so below the ground. So it is not only the exploration of minerals, but consequent to exploration. So every company generates huge amount of the waste material. So just a matter of fact, here I shown red mud, fly ash, and phosphogypsum. So these are the three major variety of the byproducts. I should not say waste products. These are the byproducts generated by three major industries. So one is by aluminium, and next is by the thermal power plants, and next is by the Paradeep Phosphate Limited, which deals with manufacturing of different pesticides and like DAP, so on and so forth. And one of the core things that I found, so when you try to deal with anything is you have to have a fair knowledge about the oxides composition or the minerals composition. In fact, so these two are interlinked. So I took one of the areas as interesting is, so though it typically falls under ground improvement, but having a thorough knowledge on clay mineralogy and oxides influence certainly helps you to understand the physico-chemical behavior of the waste materials. Okay, so all certain then you are converting the waste into the geomaterials. So once you are understanding the geomaterials, the mineralogy and oxides composition, you can definitely augment such knowledge for understanding the behavior of the waste materials. So one important thing is that when you talk about any waste material, it is certain that these waste materials are dominant with a particular oxide or particular mineral. So that's how we can able to distinguish the natural geomaterial with the waste material. So if you look at the natural, any geological material or the material which has a geological origin, so most of them they maintain some kind of the homogeneity. Like for example, if you take the soil, so the oxides composition, that is SiO2, Al2O3, RNO, so on and so forth. So they are maintained almost, if you look at any soil, so they are more or less uniform. But often we can also find there are dominance of particular minerals or chemicals in these soils also. But anyway, so just to summarize, one has to have a thorough knowledge on oxides and mineral composition. Then I'm also working on the use of biopolymers and geopolymers for sustainable utilization of waste materials. So then microbiogeotechnology, use of microbes to ameliorate the waste material. Then there is an interconnection between waste valorization and the remediation of the contaminated sites. So if you look at this topic broadly, earlier people used to talk about only the remediation of the sites which are contaminated because of the spills or something. But nowadays it is not only remain confined to decontamination of the spills, but suppose even you can treat these waste materials as one of the sources for the contamination of the soil. And how to decontaminate such a soils is also one of the core problems that recent people are encountering. So these are my couple of research as Professor Singh and Professor Amit are so appraising about having some kind of the connections to have access to the research. So right now, two research students from two NITs, one is from NIT Jamshedpur and next is from NIT Mizoram. So they are working in my laboratory. So you people also most welcome, maybe in the form of a summer internships or to have a collaboration for your master's thesis, so on and so forth. You people are most welcome. So let me go into my topic today. So my topic is entirely going to focus on how to deal with one of the waste material or byproduct, that is a red mud or called as a bauxite residue. So this is one of the byproducts generated when you extract alumina from the bauxite mineral. And the utilization of this waste is almost insignificant, which is very less than in fact 10%. So it typically falls in the range of 4 to 5. But you need to have a little bit understanding about what are its characteristics or virtues. First of all, the red mud and bauxite residue both are same, and this is the one of the materials are the waste, so solid material. So it is an insoluble. Earlier, this used to be disposed of in slurry form, but nowadays it is converted into a thickened slurry or in the form of a cake. But the most troublesome with this bauxite residue is this is one of the extremely alkaline material. So that is characterized with the pH above 9.2 and hovers in between 9 to 13.5. So, but most of the time you take any other bauxite residue, its pH always lies above minimum 10.5. While this pH is basically induced in the bauxite residue because of the addition of the caustic soda, that is sodium hydroxide, which is one of the basic material. And this addition of NaOH is essential to extract alumina from the bauxite ore. And since this material is alkaline in nature, so there are different guidelines all certain then so that stipulates how to deal with the alkaline materials. So there is a different guidelines how to store or how to dispose of the alkaline material or even how to transport these alkaline materials from one place to the another place. Now, so it is not only the problem with the disposal. So there are a couple of events or some bad events which has occurred, and there are a lot of casualties. And more than casualties, there is an immense amount of damage done to the environment, as you can see from these pictures. So the very first incident of breach of red mud pond occurred in the year 2010, that is in Hungary. Then recently in 2016 also there was one such incident in China, and in India also April 2019. So there was a failure of Muri red mud pond. So if you look at or if you Google it, you can see about these incident, and you can see or you can understand what kind of the problem that can be faced and how long its footprint will remain on the environment. So this is one of the core questions that everybody has to ponder, because it's not that key some flooding has happened and once the flooding recedes there was no problem. So but even there was a problem, so it was there for some time and thereafter it vanishes. But such is not the case when you try to deal with the waste material. We do not literally know how long the environmental, the pollution footprint remains on the environment. So this is one of the core questions that you have to ask yourself. And once it is got contaminated and such a natural ground is not desirable for habitual purpose as well as for the agriculture, it has to become some kind of the barren land. Now, so these are a few of the problems, and that maybe simultaneously or maybe independently that we have to deal. So the first thing is high alkalinity. So this may pose the problem in the form of a water pollution, or the red mud comprises of very fine particles. So there is a fugitive emission that is in the form of a dust emission, and this alkalinity and this dust is threat to the environment in various ways that you can understand. And another important thing is that as the utilization of this waste is very less, that is less than 10%, then you have to constantly store, and this storage facility need to be maintained forever, which is a perpetual problem. And nowadays, the government is increasing the regulations on acquisition of the land. They are no more giving any kind of a land. They are saying you try to manage in the form of a utilization. So in the presence of these physical waste, everybody knows about what kind of the health hazards that can emanate from these waste material. But apart from this, what are the different other problems that compel to utilize or valorize these waste materials? First, the production of these waste materials in such a large quantity and where the storage is becoming an impeding problem day by day. So it is not only the storage of the facility, and how to maintain this storage facility perpetually is a daunting task. So that is another headache. Then non-availability of the land, then somehow or other way. So most of these byproduct or waste material properties resemble that of the natural. If not, we have to make some kind of the resemblance. Then using that as a some kind of the seed, then we have to progress how to make it this more like a geomaterial so that it is rendered as a geomaterial for any civil engineering application. Then alkali regeneration, then imposed regulations, then impact on the environment. It's not that I'm only the first person who is working on this waste material. So a lot of research is going on across the world on how to deal with the bauxite residue. But since a couple of the efforts are made for the first time, so we don't know what is the effectiveness of these stabilization techniques. So it is found that a few of the techniques are ineffective. So it may so happen that when you initially treat with that technique is successful, but in the later time, because of the imposed regulations, that technique may become obsolete. So like there are some acid treatments are available, seawater treatment, CO2 treatment, but these found to be either ineffective or have some secondary problems. Uh, so when I talk about the resemblance with the natural material, one of the peculiar thing that everybody has reported along with me is, first of all, the particle size fractions. So most of the particles fall into the category of the silt and clay. They are not exactly silt and clay because these are designated in terms of the mineralogy. But in terms of the size wise, so they resemble that of silt and clay. More than that, so they show some kind of the plasticity behavior. So you can find out the liquid limit, you can find out the plasticity index of these red mud. But when it comes to the compressibility characteristics, they do not mimic that of the natural material. So this is some kind of the contradictory that you can observe in terms of the plasticity and in terms of the compressibility. And the strength is also quite low, but without the strength, we can't use these materials in engineering applications. And other problems include, is there a possibility of the leaching of potentially toxic elements or harmful elements, which may in the due course of the time get contaminate the groundwater or the surface water reserves. So these are the couple of the areas where the red mud is currently being utilized. So they are used for the production of the cement or the manufacturing of the bricks or extraction of the valuable metals from the red mud or for reclamation of the acid contaminated land or as a grout material. But overall, if you look at the utilization typically falls below 10%. So therefore, you need to do a lot of research or you need to work a lot on how to increase the percentage utilization of this red mud, concurrently addressing several different issues. For example, one of the IRC codes says that if the pH of any natural material exceeds 9. So we cannot use such material in the transportation engineering. So the core question comes here is, then how to bring it down the pH above 11 to 9? Is it so easy? Or what kind of the chemical additives that one has to add? And even if we add that chemical, then what would be the consequences on expenditure? So how much is the cost of the stabilization? Or do we alternatively need to look for some eco-friendly solutions? For example, can we use the microbes? If you want to talk about the microbes, then the first question lingers is how to identify the potential microbe. So it's a big question. So then you have to search. So once it is searched, then we don't know whether it is pathogen or non-pathogen, whether it works or not, and how long, so on and so forth. So these are the typical questions that normally arises. So when you try to deal with or stabilize the material. Now, let me give you a brief about what are the different problems that normally you encounter when you try to deal with the bauxite residue. The very first problem is low strength. So the strength is so low, we cannot directly ingest this material for engineering applications. For example, if you want to use in a pavement application as a base or sub-base course, so its strength is not fulfills. Second, so it is alkaline material. So therefore, there is an inherent problem that may arise in the form of a dispersion. Usually, this dispersion is highly interlinked with the presence of the sodium cations. Okay, more are the presence of the sodium cations, more is the vulnerability of such material for the dispersion. And what about the collapse potential? So there is a possibility. Then high alkalinity. Okay, so now we have seen 4 different variety of the problems. So 4 different engineering aspects. And these are interlinked with the chemico-mechanical aspects. Now the question arises is, so how many number of these engineering properties shall I address? Suppose if I fulfill the strength criterion, but what about the collapse potential and dispersion? So in terms of the strength, yes, I got the higher strength, but still the soil, the waste material is dispersible. Can I try to utilize, or can I need to evolve different technique? So then shall I able to address together of all these problems? If the answer is yes, again, the further question arises is how many number of additives shall I need to add? Shall I accomplish with the entire task with a single additive? Or do I need to go for more than one additive? So it's a big question, and what will be the compatibility between these additives and the compatibility of these additives with the waste material. Okay, so this is how, so it is not a single day the attempt, so the attempt shall be perpetual, so that at the end of some time we will come up with a possible solution, so which competes in terms, which is compatible in terms of augmenting the engineering properties as well as at the same time, so it economizes the cost. So for most of the waste material stabilization, initially whatever the technique it is proposed, they are inexpensive, but they give some kind of the path to encouraging the engineers that yes, there is some possibility of stabilizing these waste materials, and over the period of time they have been refined or the technology has been augmented to decrease the initial expensive from the lower cost. So as I told you, the other challenges include, suppose if I say in terms of the strength, it is okay, but how to reduce the pH? So then there was not much understanding about the chemical, mineralogical, and microstructure of these stabilized waste material. It is still a gray area. Then the limited efforts are explored for suitability of the stabilized as a resource material in geotechnical engineering. So that means once it is stabilized, again we need to ascertain, so is that stabilized material is suitable for such engineering application or not? And through my research, one of the peculiar thing that I found is, yes, we could able to stabilize the red mud. We can able to reduce the pH from 11 or 12 to the acceptable range of say 8 or 9. But the same 8 or 9 is sustained in the due course of time. or is there a possibility of the rebound, that is regain in the pH? If it is regained, then what is the other possible consequences? So these are the things that we do. Now let me give a detailed about. So under what circumstances this rebound happens, and is the rebound happens really or not, then how to stabilize it. So I'm going to talk about the stabilization of this material or conversion of the alkaline material into the acceptable geomaterial when it is treated with different additives, which include the conventional additives where we normally talk about the fly ash or the lime or the gypsum, or so quite normally say the chemicals both are organic and inorganic in nature. So we can talk about addition of the NaCl, addition of the nitric acid, or addition of the hydrochloric acid, because these are the chemicals that normally talk about when you talk about acid base reaction. Then the suitability of organic acids such as citric acid and oxalic acid. People at different platforms talk about their potential utilizing as additive for neutralizing the red mud. So apart from these, you can also go for other eco-friendly techniques like biotreatment, so on and so forth. But in this presentation, let me give an insight into the performance of these different additives for stabilization of the red mud. So these are the physical and chemical properties of the red mud. So as I told, how do you distinguish the waste materials with the natural soil? For example, when you talk about the red mud, which is a residue, the iron content is very high. So the iron content typically ranges between 40 to 55%, which is completely contrary to natural soil, because in natural soil there is a dominance of silicates. So more than 50% of the natural soil composes of silica alone, then followed by the aluminium, then other minor elements like sodium Na2O or CaO or MgO, so on and so forth. But contrary to natural soil, the bauxite residue comprises of 40 to 55% of the iron oxide. Then what are its implications on the engineering properties? So that's what should be the focus. So can this iron oxide be inert, or will it make some kind of the chemical reaction with the additives? That is also a problem, because this is the dominant oxide's composition. So here, for better understanding, I have given the chemical compositions of other additives. So for example, if you look at the red mud, it is rich in iron. But if you look at the slag, it is rich in silica and calcium, which is completely opposite to the red mud. Then another GBS, so that is also rich in silica and calcium. But if you look at the lime, so it comprises only of the calcium. So similarly, if you look at the fly ash, it also rich in silicates and aluminates. So this is how you should understand how the natural materials are distinct than the waste materials. And fundamentally, when you try to attempt any problem, such basic understanding is essential, which otherwise, even if you do some kind of an experimentation, again, you'll be forced to come back to understand all these physico-chemical mineralogical aspects. So then try to assess their compatibility. So once we have done the experimentation and coming back, it is always advisable to go from the scratch, try to understand all these, or try to understand from the vast literature, and then go ahead or evolve new kind of the additives. So these are some mineralogical characteristics and morphological characteristics. So here we can see the mineralogical compositions of the red mud. It typically comprises of calcite, anatase, cancrinite, hematite, ilmenite, perovskite, sodalite, and geotite. Now, these minerals you might not have heard. So when you compare with the soils, because in soils you normally hear about the quartz, presence of the quartz, or presence of the montmorillonite mineral. If you have studied the clay mineralogy of during the soil mechanics course, you heard about the montmorillonite, illite, mica, kaolinite, so on and so forth. Now, incidentally, you can't able to find any such kind of mineral in the red mud. So, but in terms of the particle size, we still say that the red mud comprises of the particles fractions like of clay size of sand size. So when the mineralogy is completely different, then how to deal with such material? We do not know how these minerals will react when you add the conventional additives like fly ash or lime, because these are widely used additives in geotechnical engineering. So for treatment of the soil, and these are some morphological characteristics of red mud and other additives like a lime, GBS, slag, and other materials. So now, since I'm talking about the red mud, so it is not only produced by the single source. So there are a lot of industries are there. Nalco is one of the major producer. Then Vedanta, then Hindalco, then Hindal. They have two plants at Muri. One is at Muri and one is at Malgam. You can understand. Even the chemical compositions also differ based on the what is the process that they implement for extraction of alumina from the bauxite. So there is a small distinction among the red mud produced by the different plants. So even that is also a bit interesting. So you can see one common point is almost among all bauxite residues produced by the different plants, iron oxide is higher in content. But you can see the variation. So for example, the red mud which is produced by the Indal Muri, it is as low as 25%, but if you look at the red mud produced by the Nalco, so it is almost double. So on the other hand, so these are the different additives, so which are dominant with other chemical compositions. So another important characteristics that you need to understand is, so as I told, so the red mud exhibits some kind of the plasticity characteristics. So then how to prove that? So it really exhibits some kind of the plasticity characteristics. Or if you want to understand the compatibility of any additive, one of the fundamental phenomenon that is the flocculation or dispersion, or alternatively, you have to understand about the other chemical phenomena of adsorption, ion exchange, modification, so on and so forth. One of the simple technique that can give some kind of insight into understanding the flocculation or dispersion behavior of any geomaterial is you try to measure the zeta potential of the geomaterial. So this zeta potential gives an understanding about the charge capacity of that particular material, and this charge is induced by the several aspects. Suppose if you look at any soil mechanics, they say the charge is, suppose in case of the clay, it is because of the negative charge. While in case of the red mud, it may be because of the presence of the oxides, or it may be because of the presence of the broken bonds. And as you vary the pH, so that is because of the addition of the additive, then you accentuate the phenomenon called as the flocculation or dispersion. So here you can understand what is the meaning of the flocculation and what is the meaning of dispersion. Because when you add any additive, for example, if you look at any stabilization of the expansive soil, they work basically on aggregation, that is a flocculation, while some additives also work based on the phenomenon of dispersion. Or, for example, if the chemical reaction has to happen homogeneously, the material has to be initially in dispersion state, then followed by it has to be aggregated or in flocculated state. Flocculation means the material becomes very hard. Dispersion means that every particle is in its individual state. So these are some zeta potential response on the red mud. As you can see, the zeta potential varies as you change the pH. So whenever the pH becomes zero, this is called as a point of zero charge. For the case of the red mud, it happens at a pH of 6.6. So here you can see when the pH is below 6.6, so the zeta potential is positive value, and when it is above 6.6, it is the negative value. These positive and negative value are some kind of implications in the form of a flocculation or in the form of a dispersion. But this understanding is very crucial, because if all the red mud particles are under, say, for example, below 6.5, so they are in the form of aggregates. When you add the additive, so it can react with the aggregates rather than the individual particles. That means initially we may have to maintain the dispersed state of the soil so that the added chemical reacts with all the particles, then followed by it goes to the state of the aggregate. So that is called as a flocculated, and thereby it becomes the hardened substance. So that's how we can utilize the Zeta potential results. So you can also correlate the Zeta potential with the particle diameter, which shall give a clear understanding about in what state they are available in a dispersed state or in aggregated state. So here, all these measurements are made with the help of the Zeta sizer, and you can also understand when you change the pH condition, how the same particles may be of the size of the clay or of the size of the silt, how they undergo the dispersion phenomenon or the flocculated phenomenon. So another important property that I was talking about is dispersion. So red mud is said to be highly dispersive material. Then how do you understand or determine its dispersion characteristics? So there are three methods that are available. So you can go by the visual identification, or you can go for the physical testing or the chemical testing. So one of the widely used physical tests is you conduct the crumb test or the hydrometer test or the negative differential freeze-fill test. So these are very easy to conduct and everybody can conduct. So and other chemical tests, but you require some kind of accessories. So you need to determine the pH and EC or the sodium absorption ratio or exchangeable sodium percentage, so on and so forth. So usually the physical tests are widely used for identifying as well as quantifying the dispersion behavior. So here we have conducted a lot of negative differential freeze-fill tests as well as double hydrometer tests to identify the dispersion behavior as well as to quantify how much it is. So these are the results of the crumb test, and these are the results of double hydrometer test. You can see the same particle size, but two different particle size distribution curves you can able to get. That indicates that these red mud bauxite residue can undergo the dispersion. And so these are the results of the negative differential freeze. So it's supposed to be on the positive side, but on the negative side, which indicates so these particles can undergo the dispersion. And so these are the ways of identifying the dispersion by the chemical means. So one of the chemicals means, so this is some predefined curve between percentage of sodium in pore solution versus TDS. So when you try to draw this kind of relationship, they have given some definition like dispersive or intermediate dispersive or non-dispersive. So when we superimposed our chemical results on this pre-classified scheme, then we found that the red mud falls under highly dispersive material. Okay, so this is some kind of the evidence to show that this red mud falls under dispersive nature. Then one of the remedy that we found is, suppose if you treat these materials with some kind of the biopolymers. So these are eco-friendly materials. So there are a lot of biopolymers are available. So in our study, we used gore gum as well as the jandan gum as a biopolymers to mitigate the dispersion behavior. As you can see, so when we have treated with a gore gum and put inside the water, they should able to sustain for the stipulated period. So here, suppose a stream code suggests that there should be in undisturbed state for at least 6 hours. Now, as you can see, when we have treated with the jandan gum, so the particles got dispersed, but the same when we treated with the gore gum, so the sample could able to retain its geometry for the stipulated time of 6 hours. And to understand what was the mechanism that was going inside when you add the biopolymer with the waste material is, there was that was observed by recording the scanning electron microscope graphs. Here we can see So you can see some kind of the particles aggregation. So this aggregation is typically because of the addition of the biopolymers. And a close examination also shows that each particle is coated with the biopolymer, which is advantageous. And this is a physical phenomenon. But how to ascertain that this is a physical phenomenon and this is not changing any kind of mineralogy? For that purpose, we have established their mineralogical characteristics with the help of the X-ray diffraction. And as you can see, there was no change in the mineralogical properties with the addition of the biopolymer. So this is how you should able to ascertain that there was only the physical phenomenon is going on, or the physical process is responsible for mitigation of the dispersion, and there were no changes in the chemical compounds or the chemical things that is happening inside the retina. Because if there is some kind of the mineralogical or the chemical changes, again we have to do some additional tests to understand, is it again accentuating some kind of the leachability problem, or is it so impeding the leaching problem, so on and so forth. And another way is you simply measure. One of the simple techniques of assessing the efficiency of the biopolymer is simply measure the turbidity. And if the turbidity value is very low, that indicates that the soil could able to retain its geometry. So you can see there was a drastic reduction in the turbidity value. So the moment we add gorgum as well as the gender. So that's what about how to mitigate the dispersion. Then I don't need to re-emphasize the importance of the compaction and the consolidation characteristics, but one of the peculiar thing that again we observed, so in the case of the red mud is when you try to compact this material, so with the standard Proctor compaction energy, it shows some kind of the inconsistency in gamma D, dry unit weight, and moisture content value. But the same soil, when it is done, when the compaction is done with a modified Proctor test, almost we got the similar values of the gamma D and OMC, but the initial curve shows that initially it is sensitive to the moisture content. So this is some peculiar thing. But if these are the inconsistent and consistent results, then what kind of the compaction state that you refer to when you try to apply or when you try to stabilize this material in the field? It's a big question. So then we also try to vary the number of blows to see the effect of the compaction energy, and this is what is the response. So as you increase the compaction energy, you'll get a different values of the gamma D and moisture content. And we also made an attempt to understand how this waste material, when comparison with other waste material, falls. So these are a bunch of different waste materials. So there are industrial waste, these are the municipal solid waste materials, and there is a red mud, and there is some treated soils. So here the bottom curve shows the municipal solid waste materials compaction curves. So you can understand how much water the municipal solid waste material could able to retain. It's hoping more than 100%. But when you go for the other industrial waste materials, a few waste materials showed very high drying weight but very less moisture content. The optimum moisture content is hardly anything below 10%. So in case of the red mud, it typically lies between the FU waste materials as well as the municipal solid waste material, municipal solid waste. So this is how you can able to understand how different materials behaves in terms of the compaction characteristics. So this is a typical comparison to assess the suitability of any waste material or the natural material for different engineering applications. So different codes are available. You can follow IRC SP58, IRC SP20, IRC SP22, 72, and then as the guidelines are available, MARC guidelines are available, IS code guidelines are available. So that MOD guidelines are available. So these guidelines deal with what kind of material should be selected for different purposes. For example, IRCSP50 talks about the selection of the fly ash as an embankment material. IRCSP talks about how to select the materials for earthen cover and the subgrade. So this is a short summary. You can go through it. So then there was an impact of the particle size on the compaction also. So here you can see when you have saw the particle size distribution under scanning electron microscope, we found that the red mud typically comprises of heterogeneous particle sizes. So this obviously indicates that so these particles can impact the compaction characteristics as well as the consolidation characteristics. So these are the consolidation characteristics of the red mat. If you look at the basic response, so that is the variation of the wire ratio versus log, it typically resembles that of the natural material. So that way it is advantageous. So okay, because it is not deviating from the compaction characteristics of the natural material. It's well and good. So then what about the CC value or MV value? So will there be resemble that of the natural material or will there be any deviation? So that also need to understand. So incidentally, so what we found is the red mud exhibits low compressibility characteristics even when you compare this material with the natural soil. So that is advantageous because on one side I'm saying that the red mud exhibits some kind of the plastic behavior, but any material which exhibits the plastic behavior, it is bound to exhibit high compressibility characteristics. So that's how the plasticity index is interlinked with the compression index, that is CC. You'll see a lot of correlations between PI and liquid limit with the CC. So as to ascertain that kind of a combination, so you need to have a fair understanding about the consistency limits as well as the compressibility properties. Then, so one of the core issues with the red mud is the alkalinity or the high pH. But who is going to induce these high pH to the red mud? Because when you talk about your 10+2, you typically talked about so the acid and the bases. When the, say for example, acids are dominant, then the pH is very low. When the bases are dominant, then it is the alkaline material. The pH is very high. So when you take the red mud, there are several chemicals that can induce high alkalinity to it. So those are hydroxyls, because you are adding the sodium hydroxide to the bauxite ore. So that is still remain inside the red mud only. Then carbonates, bicarbonates, then aluminum hydroxides. So then other chemicals. All these chemicals induce some kind of alkalinity to the red mud. But how and in which form they are available? So they're available in mineral forms. So for example, the sodalite, which is a basic material, which can cause high pH. Similarly, cancrinite, then hydrogarnet, then tricalcium aluminate. All these can induce, these are the minerals available in the red mud. So they can induce high pH to heat. So that's why the pH of the red mud is very high in the form of above 9 to up to 12.2. So then in order to reduce this pH, people have suggested that why don't we add some kind of the lime or hydrated lime to the red mud. So here the typical chemical reaction that can occur is with the addition of the lime, the calcium can replace the sodium and thereby it can reduce the pH. So this is one such possibility. Then hydrothermal process. So in hydrothermal process, typically we add sodium acetate. So it triggers. This is one of the best agent to dealkalize the any material. So the addition of the hydrothermal process typically involves so the dealkalization of the red mud by simply adding the sodium acetate. Then another process is, as processing was saying, one of his student is already working on so neutralization of the alkaline material by applying the gas. So you can use gas, that is CO2, carbon dioxide, or sulfates SO2. So these gases can be used to neutralize the red mud. So they will bring down the pH, very high pH above 10 to the acceptable level of below 8 or below 9. So they are one of the highly effective additives for neutralization of the red mud. This is also called as the process is called as sequestration. So that means the added gases, that is CO2 and SO2, either they will permanently retain on the particles or they will convert, they will make some kind of the chemical reactions and thereby transform one chemical into another chemical. For example, here, so the reaction of CO2 and SO2 with the hydroxides can form bicarbonates and sulfide, which can then oxidize to sulfate. So whenever there is sulfate available, this can form hydrochloric acid, that is H2SO4, which can further neutralize the red mud. So this is how the chemical reactions progress and thereby neutralize the red mud. So alternatively, people also did work on neutralization of red mud by adding calcium chloride solution or magnesium chloride solution or ammonium chloride solutions. So these also found to be one of the effective chemical agents for neutralization of the red mud. So then the previously talked about chemicals might have some kind of impact on the environment. So now people are talking about, so instead of using the pure chemical additives, which is a cost intensive process, can we go for the cost effective processes? So which include the addition of the microorganisms or the processes which are eco-friendly driven. So one of them is use of the microorganisms or addition of the inorganic acids. So here, but you need to identify the most appropriate microorganism. So, and this microorganism may be supplanted again with a chemical. It might be requirement or might not be the requirement. So these bacteria, so when they do some kind of chemical interaction, so they can either release or they can use the harmful compounds as their feedstock material. And this feedstock material, they have a chemical reaction inside the microbes, and thereby they dissociate the chemical into usable compounds. So one of the simple flow chart is given here, and there are some microbes which are typically available to produce the desired chemicals also. So it's a big research area. Then of late, the research is also going on. So development or production of the bioacids. So here, so they take some natural materials. So for example, you can take the leaves. So these leaves under a particular hydrothermal action, so they can become biomass or bioacids. And these produced bioacids are further then added with the red mud. So these are the acids. They can have an acid-base reaction with the bauxite residue and thereby neutralize the red mud. So this is one such possibility. So this is a typical flow chart that is describing about how to produce the bioacids using the natural materials. You can take any saplings or the plants or the leaves. So it is up to our choice. Do we exclusively need to use only leaves, or can we use the plant as a whole for producing the bioacids? But there is an immense scope to evolve the technology required for development of the bioacids. There is an immense scope. You can work on such a kind of the topics. And because India is rich with variety of the plants, so you can come up with your own idea of developing the bioacid with your own identified plant. It's a rich research area. So alternatively, you can also use mineral acids like hydrochloric acid or H2SO4 or HNO3, so on and so forth, or organic acids, as I told, the citric acid or oxalic acid. So these also prove to be effective in the reduction of the alkalinity or the pH of the red mud. So these are some information on how effective these chemicals are for reduction of the pH by the neutralization mechanism. So you can see the difference, huge difference, the initial pH and the final pH. So this is little summary about the alkalinity. And let me also show some results of research which is conducted by my couple of MTech and PhD students. So here we used some conventional additives and as well as organic acids. So these are the compaction results of the red mud treated with the hydrochloric acid as well as the sodium, HCl and NaCl. So, and by conducting the standard Proctor compaction test as well as the modified Proctor compaction test. So both are producing in terms of the compaction characteristics reasonably higher values of the gamma D and OMC. So in terms of that means when you treat the red mud with HCl or NaCl, so there was no impact on the compaction characteristics. So then we try to use the lime, fly ash, and the gypsum. Here we can see the compaction characteristics. So when we try to add the fly ash with the red mud, so there was almost no change in the dry density. However, there was a small change in the optimum moisture content. So that means you can understand if there was no as long as there was no decrease in the dry density, so it is well and good. So, but of course, there was no increase in the gamma Dmax. So, because almost you are trying to replace high specific gravity material with the low specific gravity material. That's one of the reasons for compensation in increase or decrease. Sorry, compensation in no change in the gamma Dmax values. Similarly, when you try to add the gypsum also in appropriate proportions, we saw there was no change in the gamma D and no change in the W art. So these are the compaction curves, but there was a mild decrease in the OMC when you add the lime content. And so these are the results of the compaction characteristics. So here we found the compaction the density is reasonably high, which is in the range of 1.64 to 1.78, and the moisture content also slightly this below 30%. And so this is how you can assess the suitability of the treated soil. This is a lime treated soil suitability as per IRC SP20 for rural roads. So then these are the citric acid treated soils. So this is for standard Proctor and this is for the modified Proctor. So when you try to add different molarities of the citric acid, so there was a clear impact of citric acid treatment on the compaction characteristics. So this is a bit contrary to the conventional additives. So this is the response of the gamma D max, and this is the response of the moisture content. Almost there was no change in the gamma D, but the gamma D yielded by citric acid treatment is much higher than the gamma D that of the fly ash or the lime or the gypsum. So that is one thing, one important observation. But there was also decrease in the WR. This is also good observation because we need less affinity of red mud oxide to water. So that's a requirement. And the same thing is achieved when you add the citric acid to a red mud. So these are the strength results. So all these results are published in ACE Journal of Hazardous, Toxic and Radioactive Material. So all these publications are available. So if you want, I can also send copy of all these papers. So those who decide it. And these are strength results. So you can compare how much is the strength improvement. So here you can show, here it is shown. So for different citric acid concentrations, the strength of untreated red mud is hardly 100 kilopascals, while it is increased to almost increased and rose up to 500 kilopascals with the treatment of the citric acid. And we try to also superimpose what is the requirement for different engineering applications. So fortunately, the citric acid treated samples complex the requirement of FHWA, but it won't comply the requirement of MRWA. And we also try to find it out the strength variation for different curing periods, for 7 days, 28 days, 45 days, 90 days, 180 days, and 265 days. So this clearly indicates what will happen to the strength improvement in the short term as well as in the long term. Now here, one of the important points that everybody has to understand is, so when you try to deal with waste material, it is not a short-term phenomenon. We have to understand its impact in the long term. This is one of the fundamental reasons. So we try to determine the strength up to 1 year. So since there was no change or the strength improvement between 180 and 365 days, we can say that okay. So now the final, whatever the chemical reaction or the posoronic reaction that has to happen, so it have happened, or it might have consumed old chemical that has used for a treatment purpose. So these are consolidation characteristics. So they perfectly resemble that of untreated red mud waste or the natural geomaterial. So there is no deviation. So therefore, so we can conclude that the citric acid treatment doesn't impact the consolidation characteristics of the red mud. So these are collapse potential, as I told. So there is a, since the red mud exhibits the dispersion behavior, so the collapse potential behavior also cannot simply be disregarded. So it is our duty to ascertain that there was no collapse potential of the treated soil. So with that reason, we also conducted some collapse potential test along with the dispersion test, and we found that so with the addition of the citric acid, there was a drastic reduction in the collapse potential. That is well and good. So if it suppose say again, incidentally here what happened is when you added 6 molar citric acid, it suddenly aggravated the collapse potential, which is a little danger. That means when the molarity increases to 6 molar, it is doing something else. So that means the addition of up to 4 molar is good enough. You should, by no means you should use the 6 molar. So these are some negative effects. Up to 4 molar, there is a positive effect, but behind 4 molar, so there was a negative effect. So this is how one has to understand what is its impact on the collapse potential. So then another most important thing is, since I told it is an alkaline material with the addition of the fly ash in different compositions, what will happen to the pH? Will it increase or will it decrease? So these are the results. So we have done an elaborate testing of red mud amended with the fly ash. So whatever the composition you take it, the addition of fly ash doesn't mitigate the pH to the desirable value. The desirable value of the pH is 8 to 9, but as we see, the pH never came down below 10, so which is not acceptable. That means, so the addition of the fly ash or the gypsum, their combination, whatever you talk about. So it is not useful in a sense of mitigating the pH. While you may have to think of how effective the addition of the fly ash and gypsum in terms of the strength improvement that you can think of. But in terms of the pH reduction, we can conclude that these materials are ineffective. So then other combinations, so you can see the addition of the lime. In fact, when you added the lime, so there was improvement in the compaction characteristics, but there was no relief from the pH. The pH is in fact increased. So instead of decreasing, it has enhanced the pH. But with the addition of the fly ash and gypsum, the pH is about 10.5. So, but our acceptable range is 8 to 9. This is as per the IRC code. So that means we can conclude again here that with the addition of the lime or the fly ash or the gypsum combination, so we don't get any benefit in terms of the pH reduction. So these are the other results, the same on the pH measurement. So then the performance of other inorganic acids like HNO3 and HCl. So here you can see one of the peculiar phenomena that that we could able to determine is when we have mitigated the pH from above 11.5 to acceptable range of below 8. Now here you can see with the addition of HNO3, so HNO3 the pH 1, pH 1.5, 2 and 3. So then HCl of pH 1, 1.5, 2, 3 and 4. So when you add HNO3 equivalent of pH 1, it successfully reduced the pH from above 11.5 to 7.54. So 7.54 is acceptable range. But since we are dealing with the waste material, it is our responsibility to check. So is the same thing is sustained for the long term, or is there any reversal in the pH? So here you can see, so there is a pH reversal that has happened, and after 45 days, it has exceeded the prescribed, the acceptable range of 8 to 9. So then what will happen? So after 90 days, now there are no codes available also what to say whether this material is acceptable or not when there is a pH reversal. So this is a tricky situation. Okay, so then there are other associated problems also, so that people has to think of. So when you add the HCl also, the same thing has happened, but with the HCl, the rebound of above 9 has occurred within 28 days only. So that means when you compare the performance of HNO3 with the HCl, HNO3 is a bit better, but not useful. We can say ineffectual. Similarly, with the addition of the gypsum, so these are the results. So we can conclude that addition of 1 and 2% of gypsum is completely useless because it could not able to reduce the pH. But when you add higher doses of the gypsum, say 4, 6, 8, 10 up to 12, they are effectual. And in fact, when you compare the performance of the gypsum with the HNO3 and HCl, yes, it could able to perform. So even after 90 days, So the pH is still within the acceptable range. So that is well and good. So then we try to quantify how to quantify the pH rebound. This is one of the novel parameter that we proposed. So that is how to quantify the pH rebound. So for that purpose, we have drawn several graphs. So here you can see the variation of the pH with the curing period, and for different molarities of the citric acid as well as the oxalic acid. So this is addition of the citric acid alone and the citric acid oxalic acid alone. So these are the different results. You can see initially, so the curing period is 20. So the between 8 to 9. But as time progresses, you can see there is an increase in the pH, and after some time it also become almost constant. But how to interpret this data? So what is the meaning that we can take out? So from these graphs, so I can clearly say two things. So this is a first of all bilinear in relationship. So that means up to approximately certain time, up to say year 40 days, there was a rapid regain in the pH, followed by some kind of plateau, that is saturation, or the pH is becoming the constant. So what is that meaning? So what these two, the rapid initial increment followed by the constant indicates, and what is this time period indicates? So this is how we have quantified so the pH rebound, and we can also see the performance, relative performance between the citric acid and the oxalic acid. So when you compare the citric acid and oxalic acid, we found that oxalic acid is performing bit better than the citric acid, as you can see. So in case of the citric acid, the pH is lie between 8 to 9, the initial pH. But when you add the same molarity of the oxalic acid, the pH is even below 8. So it is a good. And in fact, when you talk about the pH reversal also, there was more reversal happened in case of the citric acid, and the rest reversal has happened in the case of oxalic acid. So then we can say that, or we can recommend that use of oxalic acid is preferred over the citric acid. And so this is how we have quantified. And these are the results pertinent to combination of the organic acids along with the lime. Now here we also try to add the lime, because as I told, we need to address the multiple properties. So pH is one of the concern, as well as the strength is another concern, collapse potential is another concern, and dispersion is another concern. So what we did observe is, when we added oxalic acid or the citric acid, yes, so there was a decrease in the pH. We could successfully able to mitigate the pH or address the alkalinity criterion, but we could not able to impart desirable strength to the material. So then what we thought is, since we extensively use lime and lime fly ash or cement as an additive for strength improvement. So why don't we use combinedly lime and the organic acids, so that we can attack the reduction of the pH as well as the strength improvement. So with that intention, we have added 0 to 10% of the lime. So for different molarity of oxalic acid as well as the lime. But in fact, we got the same pH rebound in this case also with the combination of the organic acid and lime. So we got some bilinear relationship, and we try to quantify by trying to fit two bilinear curves, and the intersection is termed as the time required for the rebound. Or so this intersection indicates, so it may be time required for cessation of the pH rebound. So through our study, through our extensive results, so we found that the rebound is rapid up to a time period of 45 days, and behind that it is almost becoming constant. And we found that 1 and 1.5 molarity of oxalic acid treatment is useful. And if you talk about the combination, a combination of say 1 or 1.5 molarity along with 5% of lime, we found as highly effectual in multi-purpose. Say in strength augmentation as well as sustaining the pH rebound, because both are important. But of course, once the strength is improved, we also found that these combinations are also effective in avoiding the collapse potential as well as the dispersion. So in terms, suppose I can conclude that with the addition of the oxalic acid as well as the certain percentage of the lime, we could able to address all the four issues. One is strength improvement to the desirable value that we attained, mitigation of the pH, we achieved the below acceptable level, that is below 9. So then we successfully avoided the dispersion problem as well as the collapse potential. And further to add quantification, so one specific parameter that is called as the rate of rebound. So rate of rebound means, so here I showed we fit one linear curve to the initial rapid rise of the pH rebound. So this, the slope is we term as rate of rebound. So this slope we further drawn along with the molarity, because we need to understand which molarity is highly effectual. Because we did use 4 molarity, 1, 1.5, 2 and 2.5. So which molarity performed highest? And these are the complete summary of results. You can see red mud with citric acid alone, how rate of rebound is happening, and approximately what was the total time period for the rebound, then what is the total pH rebound after 180 days. So this is a summary. Then red mud along with oxalic acid, then red mud and oxalic acid plus 5% lime. So here you can see the variation of rate of rebound with the molarity. So at approximately 2 molar, the rate of rebound is immensely low. And at 1 and 1.5, the rate of rebound is slightly high, and it is especially high at 1.5, and there onwards it has decreased. But from our studies, we found that for the combination, so everything is almost, there was less rate of rebound and lower, slightly higher period of time required for rebound, and total pH after 180 days. So for the combination of oxalic acid plus 5% of lime is highly effective. So then one of the important thing is when you try to talk about the stabilization or the addition of any chemical additives, so you have to clearly understand what were the changes in mineralogical composition or what were the changes in chemical composition. So here, is the mineral remain as a mineral? There are two things. A complete transformation of a mineral can occur. So, say for example, the calcite can entirely be transformed into another mineral, or there is something called as a phase change. So the same mineral is available in different forms. For example, if you look at Al2O3, it is available in 3 or more than 3 forms: alpha, beta, or gamma. So there was no problem with the alpha phase, and there was no problem with the beta phase, but there was a severe problem with the gamma phase. I may be wrong also, please look into the literature. So one of the phases of the aluminum oxide is some negative effect. It increases the volume. Okay, so those are called as the phases of the same mineral. So you need to have a clear understanding about, is there transformation of the complete mineral or is there phase change within the same mineral. So for that purpose, we have tried to establish the X-ray diffractograms. As you can see here, the X-ray diffractograms for raw red mud as well as the same red mud treated with 5% lime, and the combination of the 5% lime and 2 molar oxalic acid. So if you look at carefully, there were changes in the peak intensity. These are called as the reflections. And there should not be any change in the peak intensity, that is height of the peak, and the base width of the peak, as well as the overall area of the peak. If any of these things are happening, that indicates that something is happening to that particular mineral. Maybe there is a dissolution of that mineral, or there is a phase change of that mineral, or there is a transformation of that mineral. So for example, if there is a complete absence of the reflection, that indicates that that particular mineral has completely transformed from one mineral to the another mineral. See, for example, here at between at approximately 15. So the reflection here, it is a number 3, but when it goes to red mud with the combination of 5%, so it is completely transformed. You can see this peak is completely absent. So that means something has happened at mineral level or at chemical. So this may be positive or this may be negative, because in a sense, when the strength is improved or the strength is augmented, but how to relate the strength improvement, that can be related in the form of some gels which are called as a calcium silicate hydrate or calcium hydrate, the calcium aluminate hydrate or tricalcium aluminate, or a tringite, formation of the tringite, formation of the starting light, so on and so forth. These are called as the cementitious gels or cementitious minerals. So presence of these minerals are important because these are the strength imparting minerals or strength imparting gels. Identification of these chemicals or these minerals indicates some positive sense. So these are the same X-ray diffraction patterns for the red mud treated with different compositions of the lime. So from 0.5, 1, 2, and 3. So there was a definite change in the mineralogical composition, which indicates or maybe strength improvement or maybe why the pH is not improved, so on and so forth. And we can also see the formation of gels like calcium silicate hydrate or calcium aluminate hydrate or tricalcium silicate, so on and so forth, or startingite or etringite. So then we also try to establish the morphological characteristics. So here you can see the very first picture on the left side top is raw red mud, and on the right side is lime. And when you try to add lime with the red mud, so how they chemically react and how they change the morphology of the red mud. So you can see a lot of aggregations. So these aggregations indicate some kind of the flocculation. We can interpret inference. We can make inferences in the form of formation of the flocculation or aggregated structure. Or if you do this SEM analysis on a chunk, you can understand how they are making some kind of the interlinks, or how intact the material is it, or how pulverized the material is. So, here you can also interlink the morphology with the mineralogical composition. One such example is clearly shown here, how to understand the dissolution of the minerals. So especially when we added 4 and 6 molar citric acid solution, it has completely dissolved one mineral. Maybe in this case it is a calcium. It is a calcite. It's calcium. So such things may be encouraged or may not be encouraged, but you need to have a fair understanding. So this is what about my complete presentation. So in detail, so this is a short summary about the different results that I have presented. Yeah, so you are most welcome to force. If you have any question, if you could able to understand, that is well and good. If you can't able to understand, you can ask me wherever you could not able to understand. Yeah, I hope I stick to the time.
Thank you, sir. Thank you very much for your excellent presentation.
Thank you so much, sir.
And I have some 2 questions regarding this.
Yes, sir.
So one of the question is that when with respect to this bauxite residue,
Yes, sir.
where you told that the pH is generally in the range between 9.2 to 13.5.
Yes.
So mostly it is towards the nature of, I mean to say, acidic.
Basic, the alkalines.
Yeah, that is a basic part. But sir, that is the only reason that is the 2 chemicals or the 2 ingredients which you have added. One was the citric acid. Okay, so that means the purpose was purely with respect to remove the alkalinity, sir.
Yes, the primary purpose was only to mitigate the pH, because The IRC code says that unless you bring down the pH to below 9, you can't recommend that material in any of the transportation engineering applications. With regard to geotech, there are no guidelines available, but I think same uh, same rule we can prescribe to even geotechnical applications also.
Okay. Another thing, sir, that you also told that the behavior means the soil is having a little bit plastic behavior.
Yes.
But as far as when the compressibility characteristics are compared, it shows very less value.
Correct, sir.
In one of your slides also you showed the dispersive nature of that material.
Yes, sir.
So, sir, is it so that the process by which this bauxite residue is coming from the plant of that particular company? Okay, so
Yes.
the process is such that due to the means the particular minerals which are present in that material are restricting for the development of any bond between the two soil grains, because even your compaction characteristics was also resembling the same thing.
Exactly.
Okay.
Because when they extract alumina from bauxite, they digest the bauxite ore. It's a typical process.
Okay.
And they use high concentrated sodium hydroxide.
Okay.
So this completely dissolves the all chemicals, because unless you dissolve, you cannot extract the aluminum.
Okay.
Okay, so when there is a complete dissolution, and once alumina is extracted, and the remaining residue again they will convert into the residue only. So in that process, all these things happens.
But sir, is there any process available where any sedimentation phenomena can be made?
Sedimentation phenomenon.
Because, for example, if I'm just thinking on that way, that
Yes.
if I try to sediment these deposits, okay,
Okay.
in some or the other way,
Hmm.
then there is a possibility that the later on the material which gets collected, okay, then its conversion will become more easy. That is what I mean to say here.
Yeah. But to my knowledge, I did not find anything because there is a process called as the Bayer's process that typically they use. There is another process also, sintering process. Sintering process is advantageous, but I don't know why they won't. I think it is too expensive, the sintering process. So therefore, the cost effective process is Bayer's process. Sedimentation, that they do not do any kind of sedimentation.
Okay.
And again, even if you talk about the sedimentation, and they also add lot of flocculating agents, and that is
Okay.
also one of the costly affair in bauxite industry.
Okay, sir. So, any more questions from participants? Any?
Participants can post their questions in the chat box as well.
Yeah, it's Saeeda Sayyed. Please ask your question. Saeeda, are you audible?
Yeah, okay.
Saida, you seems to be you have raised your hand. So do you want to ask something? If, you can post your question in the chat box as well.
So maybe you may have to unmute him.
Shalini ma'am, can you unmute Saida, please?
Yeah.
Sir, am I audible?
Yes, yes, madam.
So there is a question from Ruthvik. He's asking if we want to use RE wall for waste landfill instead of earthen bunds, what are your suggestions for providing bottom and side liner below the waste?
Oh, very good question. Yeah, so in fact, because of its particle size characteristic, where it typically comprises of silt and clay size fraction, its permeability is very low. And in fact, people found that the red mud could be one of the best material as a liner material. So at the bottom, especially at the bottom, we can forego about the top covers, but it is also a good material for the barrier. Some research has already done. It's a very good material as a liner material. But one important thing is that in terms of the permeability, so it may be fulfilling, but in terms of the leaching characteristics and chemical compatibility, so these are the two things people has to understand. So when you try to assess its suitability as a liner material.
Okay.
Sir, okay. Hello, sir.
Yes, yes, yes.
Sir, what I wanted to know is, in case if we are using the RE walls, the slope of that walls will be very negligible. Almost it is going to be vertical. So, so if you want to provide the liners, I mean, in case of bottom, I mean, bottom it is fine. But when we want to provide the side liner for a RE wall, it will be difficult to provide.
But you don't require any liner at the side. Rather, you can use this as a after modification as a fill material.
Okay.
Okay, so means this is a twofold problem. One is assessing the red mud as a fill material. So for that purpose, you have to go for the mechanical compaction characteristics. And at the same time, if you want to use the red mud as a bottom liner, then you have to go for other characterization, which is more of environmental concern.
Okay. Okay, thank you.
Yeah, first one is geotechnical concern. The second one is environmental concern.
Right, sir, yes. Thank you.
Yeah.
Hello.
Hi, madam.
Any more questions? Saida, do you want? Saida, what is your question? You can. Have you raised? You have raised the hand, Saida.
Can you hear me?
Yes, yes.
Yes, Dr. Rao, I wanted to ask that since fly ash and red mud both are alkaline wastes,
Yes,
what
yes.
will be the reason to add them and check their stability and
Saida, since there is some audio problem at your end, we would be grateful if you could post your question in the chat box, Saida. Please kindly do that. Your voice is not perfectly audible.
I'm not able to access the chat box.
Okay. Shalini ma'am, could you please see why she's not able to access the chat box?
Madam, actually, you have to log in using the credentials we have provided you. That is why you are not able to see the chat box. We have given you a unique number. Like here it is, as you can see in the display, it's a 0304. So you will have to use that ID. Then and then you can access the chat box.
Am I audible now?
Just try to reiterate your question. Maybe you might just increase the volume. Hopefully, you will be audible this time.
Okay. I just wanted to ask that since fly ash and red mud both are alkaline wastes,
Yes.
what would be the reason for adding them and seeing their characteristics if they possibly cannot reduce the pH of the composite that we get?
See here, fundamentally, when you envisage any kind of a pH reduction, so literally there has to be chemical reaction between them. And this chemical reaction usually happens in the liquid form when aqueous solution is available or when aqueous solution is in contact with both the materials. Or alternatively, you have to get dissolved the desired chemicals from these two solid materials. So here what we found is, in fact, when you add the fly ash with the red mud, such a dissolution is not happening to mitigate the pH. There was no chemical reaction between the red mud and the fly ash. And the fundamental reason why we have selected fly ash is because its generation is so huge quantity, and everybody's mind as a first solution comes is, sir, why don't you use the fly ash as a additive? So with that intention, we try to use it. But when you simply add under ambient condition, they may not be working. But for example, you can go for the alkali activation of fly ash with the red mud. It may work. It may work because there you are adding additional alkaline solutions. So that may catalyze the chemical reaction between red mud and fly ash. There is a possibility.
Thank you. Thank you very much.
Yeah.
Okay. Do we have any more questions? It's an earnest request. Again and again, we have been mentioning that please log in with your credentials. Otherwise, you will not be able to access the chat box. But still, for all those who are still not operating from credentials, if they have any questions for Dr. Rao, kindly post it. Kindly speak it out.
Okay, thank you, sir. Thank you very much.
Thank you so much, sir, for giving this opportunity.
It's our